Today's the day. This is the day that we learned the shortcut on trying to solve these equations without having to use a graphing calculator. Now I've merged two lessons in one here since this is review, and the main thing I want to talk about today is how do you solve logarithms. Well, there's three properties that might come in handy as we're doing that, and I went ahead. In college algebra you would have spent a whole lesson on learning these properties. I'm just going to go over them and then move forward. If you look at, these are the three main properties that we use. And if you look at this first one, what this says is that if you have the log of two things being multiplied together, you can separate that into two separate logs and add them. Okay? And similarly, if you're taking the log of two things divided, then you can separate it into two separate logs and use subtraction. And then the third one has to do with taking the log of something raised to a power. If you raise that up to a power, it basically is multiplication by the same thing over and over and over. And so what we can do is we can take this exponent and bring it out in front and say, well, I'm going to do that log that many times. So it looks like this. We'll use these properties of logarithms as we're solving equations today. The first part, and so I am going to practice those properties a little bit at the beginning so that we know how to do that. So this first one is the natural log of 5x squared. Well, we're multiplying two things in here, plus we have this power. To do this, I'm going to separate this. This is called expanding. I'm going to come way up here because I'm afraid I'm going to run out of room. I'm going to separate that into the sum of two separate logs. So I'm going to add, and it's going to look like this. But then I also have this squared, this power, that can be pulled out in front, but only out in front of this first one, because that's the only thing that's getting squared. So final answer on that one would look like this. Just expanding that logarithm. The next one, a little messier. It's division. I see the big fraction bar. Let's start there. Let's separate it into the square root of 4 plus x cubed. And I'm going to subtract the log of 12. Now the log of 12 is done, but this first thing, you can look at this quantity that is being square rooted and think of it, put in parentheses, with a power of 1/2. Which means I can pull a 1/2 out in front. Make sure that you keep parentheses around that 4 plus x cubed because all of that is being taken the logarithm of. If you don't have that, it would look like you're only taking the log of 4. And then separately, you're adding x cubed. It would be tempting here to try to do something with your x cubed or this addition, but remember, we're expanding this. I don't want to turn this, I'm trying to gain some addition like we did right here, or like we did here, to gain that in there. So I'm not trying to get rid of the addition. Plus the cube is on this, which is part of the addition. If it was out here, I could pull it out in front. But when it's just on the x cubed, there's really nothing I can do with that. I'm done with that part of it. And just add in that last part, and we'll call it good. This next one is the one that's really kind of tricky. It's got a lot going on. I'm going to first, I don't know, gosh, there's a lot here. I'm multiplying right here, and I'm multiplying right here, and I'm multiplying right here, but this is caught up with that square root. I'm going to go ahead and separate this out into the addition of 3 separate logs, with the 7, with the x, and with this mess. And I don't know, how good are you guys at this? Well, you know, once you've done this once, you can start doing a lot of that in your head. Like I was contemplating going ahead and putting my 1/2 right here. If you could do that in your head, that'd be all right. In fact, just for the sake of space, I might have to do that. But I've probably lost my chance to erase. Sorry, it's kind of temperamental. So here I go. Log of 7 plus log of x, plus, put the 1/2 in front, and then I'm going to have the log, and in parentheses, 5x. And now I've got this separated with multiplication that I could pull apart again, but I'd have to be sure that this 1/2 goes on both parts of it. All right, here we go. One more. Log of 7 plus log of x plus 1/2 log of 5 plus 1/2 log of x. And I'm probably going to call that good because I'm trying to expand this as much as I can. I do notice there's some like terms, like this log x could be added together with this 1/2 log x and call it 3/2 log x. These are just numbers, but remember, we're expanding. I'm not looking to merge it back together. I think I'll just leave it. That's probably fancier than anything we're going to come across anyway. Okay, that's expanding logarithms. Let's try condensing logarithms. That means you're going to already see the addition, subtraction, and you're going to try to smash that back together, back to multiplication or division. On this first one, that subtraction is going to turn into 8 over, I'm going to do this one in my head because remember this 3 is going to come up here as a power. So that's going to turn into an x cubed, and that's what I'll have in my denominator. Log base 7 of 8 over x cubed. The second example has 3 separate terms in there. I'm going to do a couple things here in my head. I'm going to bring this up as a 1/2 right there. I'm going to bring this 4 up as a y to the 4th. So keeping that in mind, when the 1/2 goes up there, that's going to be a square root of x. Natural log. I'm going to have a square root of x plus the natural log of xy minus the natural log of, oops, ran out of the room, sorry, y to the 4th. Now we'll get rid of the addition and subtraction by turning those into multiplication and division. It's going to be the natural log of the square root of x. It's going to get multiplied by xy. You may want to put that in front of the square root of x. Either way is okay. But the next part is being subtracted, so that'll turn into division of y to the 4th. When I look at this, I notice that this square root of x is being multiplied by this x, being multiplied by this y. This y and this y in the bottom actually can reduce. Let's go ahead and do that. That y could cross off with one of those and turn that into a 3. And now I think I'm ready for my final answer, the natural log. I'm going to put that x in front of that square root of x, and it's going to be over y cubed. There we are. Our job today is mostly going to be trying to use some of those properties in the process of solving. Since we're solving, we are going to want to be able to type some numbers in our calculator that maybe aren't always common log or natural log. That's the only button we have in our calculator. So what do you do if you have a base 7 or base 5? Well, we use our change of base formula. If I want to find the log of some base here, of some value, and we'll assume this must not be common log or natural log, all we have to do is we take log of any other base. We typically just use common log since that has the button we need. We're going to take log, common log of x, that bigger number, and divide it by the log of your little base number. See that? If I have something like log base 3 of 7, I would type in my calculator log 7 divided by log 3. And whatever that would get me, I didn't do that one, but you would type it in your calculator and get your answer. One thing you want, I gotta acknowledge, is that some of you will have calculators that do these bases, and you can type in your calculator log base 3 of 7. Others of you have to do change of base. I don't really care which method you use as long as you can evaluate logs of bases other than 3. Let's do a couple of these, but I always like to try to estimate so we can make sure that our answer makes sense and it forces us to use our brain a little bit. 4 to some power is 100. Not going to come out nice. But I know 4 squared is 16. 4 to the third is 64. I'm guessing it's going to be pretty close to 4 to the fourth. In my calculator, I'll type log of the 100 divided by log of the little base, log 4. If I type in my calculator log 100, be sure to close that parenthesis when you do that, divided by log of 4. I get a 3.3, so it was somewhere between that 3 and 4 that I kind of knew was going to happen. I'll write 3.32. Log base 6 of 28. Do it mental math first. What would that be about? And then check it in your calculator. It should be less than 2 because 6 squared would be 36 and would already be too big. So let's see what we end up with. I got 1.86. Again, something that we're going to need if we're going to solve equations today. As we start solving equations that are going to be exponential or logarithmic, we have some methods to do that. One major method is going to be doing what we did yesterday, where we switched between logarithms and exponentials. We will do a lot of that. There's another method you can use, and that's called a one-to-one property. To use a one-to-one property means that you're going to set one exponential to another exponential, or one log equal to another log. In this example, I'm going to set an exponential equal to an exponential. As long as those exponentials have the same base, the only way these would be equal is if their exponents happen to also be equal. If you can get it down to this stage where you have the common base, you can set your exponents equal to each other to solve. But it's probably not going to sit there quite as nicely as that one did. If you look at our example here, you're going to start peeling stuff away from that exponential. The first thing we should be doing is dividing by 20. Let's get rid of that. Now we have a 1/2 to the x over 3 equals a 1/4. Now as I look at that, and I notice that this 1/4 could be written as a 1/2 squared, and then I would have common bases if I did that. I also could turn them both into 2's, where I would bump this up and make that negative. I don't necessarily see the necessity in that. I'm just going to stick with the 1/2. So that way I won't have to mess with the second fraction, or I'm sorry, the first fraction at all. I'm going to leave it be. This one I'm going to turn into a 1/2 squared. Now it looks like this here, where I have the common base. Now I'm just going to set my exponents equal. Set x over 3 equal to 2. X over 3 equals 2. Multiply both sides by 3. X is 6. And we've got our answer. It also works with logarithms. If you have one log with the same base equal to another log with the same base, then these values here have to be equal to one another. This only works if you have it simplified down to log equals log, and not any extra stuff in there. If you look at this example, there's a lot of extra stuff. Typically what we'll do is use those properties to condense that down to a single log. This whole thing right here, I would love to be able to condense to a single log. Let's see if we can do it. I know this 2 could pop up here as an exponent. I know this subtraction could turn into division. Down to a single log, I'd have an x plus 6 on top, divided by, I'm going to bring this 2 up here, and that's going to turn into a 5 squared, or a 25, equals natural log of 10. I'm ready. I've got a log equals a log. Ditch the logs and just set these values equal to each other to see what x would need to be to make this work. Multiply by 25. Subtract the 6. And we've got it. Let me just start throwing some equations at you and see if we can figure out together, of all those things we've talked about, what would be appropriate for solving your equation. Looking at this first example, I'm always trying to solve for that x, so let's just start peeling stuff away. I think I could get rid of this 3 pretty easily. I could get rid of the 2 pretty easily. Let's see what happens when we do that. If you subtract the 3, divide by the 2, and now here's where we're kind of stumped. I have this exponential. I don't really have a one-to-one property. I can't really write both sides with a base e. This is a classic example of just switch forms. Right now it's an exponential. Use what we learned yesterday to write it as a logarithm. It's a log, base e. I'm going to write it as natural log then, of 3/2 equals your exponent. Well, that pretty much isolates the x for us. I'm just going to take the natural log of 3/2 on my calculator, and I got a 0.405, which I know is now going to be a negative 0.405. Example 2. This one doesn't have too much going on. It's pretty much just a logarithm. It happens to be a common log because there's no base in there. I think we could just switch forms. Just do the big loop. It's a base 10 to the 6th power equals x cubed. Now that I look at that, another option might have been to do the property where you bring the 3 out in front and you could divide both sides by 3. That could have worked as well. I'm going to stick with what I did here. You might like that other way, and that would be absolutely fine. We will find that there's more than one way to do it. I'm just going to do the cube root of both sides. That'll isolate my x. When I take the cube root of 10 to the 6th, I get 10 squared. X is 100. One more. This one is a logarithmic equation. And again, I think I'm just going to jump in and switch forms. Do the loop and see what we get. 4 to the negative 1 power equals x minus 5. Add the 5 to the other side. Keep in mind that a 4 to the negative 1 is really just a 1/4. End up with 5 and 1/4 is equal to x. You could write it as a decimal if you'd like, or leave it, either way. How about if you try some without me? Looking at this first one, it appears we're going to be doing some property stuff because there's so many logs in there. Try to do some condensing first. The second one is an exponential. Let's see if you can come up with some method to solve this. Go ahead and pause the video. Really, I'll wait for you. Go ahead. All right, let's see what happens if we try to solve these together now, because I know you already did it on your own. Condensing. This is going to stay put. This is fine. This could pop up as an exponent. That's going to come up there and turn into an x squared. Then that would be gone. But the addition means I'm going to turn it into multiplication. I have log 10 equals log of 6 times x squared. We managed to condense it, so now we'll have a log equals a log. That's our one-to-one property. When you have the log equals the log, you can ignore the logs and just grab the two quantities and set them equal to each other. Divide by 6 would be 10/6 or 5/3. And then square root both sides. Probably going to go ahead and just get a decimal on this. And I have a 1.29 for an answer on that one. On your second one, you would have subtracted your 8. And then right away, you're stumped with this x up here as an exponent. Let's switch forms. Change it to a logarithm. It's going to be a log base 3 of 2 equals your exponent. I've isolated the x. I end up, though, with this log base 3. This looks like something I'm going to have to do my change of base formula or somehow figure out how to get this on my calculator. Change of base would take log 2 divided by log of your little base. In my calculator then, my calculator does not have that handy-dandy feature where it can use any log, so I still do my change of base. I have 0.631. Last one, I saved the best for last. Tomorrow we get to spend quite a bit of time doing formulas of different types. Today we just have this one. This is Newton's law of cooling. Isaac Newton came up with this formula as a way of determining how quickly something cools off. And it might be pizza or coffee or just boiling water, who knows. Here's our formula. The first one, this is the temperature at time t. Typically, that's like your ending temperature. T sub O is your initial temperature. Here's another T sub O. Oh, I'm sorry, that's a T sub M. T sub M is your temperature of your surrounding medium. That is your, like your room temperature. T sub O is your initial temperature minus your surrounding medium or your room temperature times E to the negative KT. Well, E is just a number. T is your time that it's cooling. K is a constant that is specific to whatever it is that's cooling. If it's pizza, it has a certain K value. If it's coffee, it has a different K value. The problem they're giving us here says that we have a coffee cup that has cooled from 99 to 55 degrees after 8 minutes in a room at 20 degrees. That information right there, they've pretty much told me everything. The problem is that I do not know what the K value for coffee is. I'm going to use this whole scenario to determine what the K value for coffee is. That will allow me to come back and do the second part, which says how long will it take to cool to 35 degrees. Well, it's only gotten to 55 degrees, so we're looking for it to cool off more. Let's do this in two parts. Newton's law of cooling is kind of a lengthy problem to do because you always do it twice, and it's a big old hairy formula that takes some algebra, which is fun, really. Here we go. Let's go find K. Using everything, all the information in pink, we have a cup of coffee that cooled from 99 to 55. My ending temperature is 55 then. After 8 minutes in a room at 20 degrees, so my surrounding medium is 20, plus, in parentheses, the initial temperature was 99, minus the surrounding medium, E to the negative K, and it took 8 minutes to do it. Right there. Now you have to start peeling stuff away to get to that K. The first thing I would do is subtract the 20. I'm going to go ahead and do my 99 minus 20 would be 79. E to the negative, I'm going to call it 8K. Let's get rid of the 79. This is going to be the thing where I'm going to write a couple decimal places, but I want to keep all the decimal places in my calculator. And now we're kind of to that point where we've got to switch forms. The K is caught up there as the exponent. I've pulled as much away as I can. Let's switch it to a logarithm. It's a base E, which means I'll have natural log of 0.44 equals negative 8K. I can just type natural log second answer in my calculator. and then divide it by the -8. K is equal to 0.102. Oh my goodness, what was that? Now I write the K equals 0.102, but I'm going to keep the entire value, and in fact I'm going to have to do some math, so I'm going to lose that number. I'm going to go ahead and store it right now. I'm going to go store alpha K. I'll have that number when I need it later. We're going to start all over with Newton's law of cooling one more time and look at the second scenario so we can actually solve this. The ending temperature, we want it to be a 35. The surrounding medium is still 20, plus the original was still 99, e to the negative 0.102. That's the K value. What I don't know this time is the T. It's to the T, sorry, you can hardly see that, 0.102 T. It's going to get solved exactly the same way. It's just that this time I know K instead of T, but they're both that little exponent. I'm still going to start off by subtracting 20 and doing inside the parentheses. I'm going to divide by the 79. And then I'm going to switch to a logarithm. And divide by the negative K value. In my calculator, I would type natural log of second answer. I still have that number sitting there. And then I'm going to divide it by negative alpha K. I don't know that it makes a dramatic difference if you just start using those rounded off numbers. I just always feel nervous with exponentials because they start to take, you start to notice that rounding after a little bit on exponentials. I have 16.33. Now let's think about what that means. How long will it take it to cool? Well, we're measuring in minutes right now. It would be 16.33 minutes. If you wanted to get really good, you can convert your 0.33 minutes into seconds, and you can wow me. Make sure that you have taken some nice notes on this Newton's law of cooling. You have a couple of them on your homework, but it keeps coming back to us, and it's like 2 problems in one. It's one that you want to know how to do. Hint, hint. Good luck.